can start. So tonight we are going to give you some general news. It's been a while that we didn't have made this kind of meetings. The goal of this meeting is to have a discussion about these 5 points, well, 4 main points. So we will start. We decided in the Kilonova-Catcher team for this kind of meeting to start with, for the newcomers, to start with like a 15-20 minutes short reminder of what is GRANDMA, what are gravitational waves, what is the Kilonova-Catcher about, etc., etc. So I'm sorry for those who knows everything about Kilonova-Catcher, the GRANDMA collaboration, etc., but I will have to make it this next 15 minutes. So it should be Alain Klotz, but he's not available tonight, so I will make it for him. And then we will try to give you few feedback about the Ready for 04 training campaign. For those who participated to this campaign, it was the last summer 2021, and it was about following up some optical transients detected by the American survey ZTF's Wiki Transient Facility. So we will try to make a summary of what has been done, etc. Then I think the main point of this meeting is to try to make a final demonstration of the Kilonova-Catcher website, a kind of how to register, how to do things, etc., etc. So I will try to make it. And I apologize in advance if we have some bugs or things like that, but I will try to be as smooth as possible for this demonstration. And finally, we will finish with, we will give you a short introduction about the new training campaign we are organizing right now, about gamma ray burst follow-up. We will give you some words about that, and we, of course, would like you to participate to this if you wish. It would be great for training yourself about following up some identified transients. And finally, we will finish with some free questions or discussions or whatever you would like to discuss. We will try to save time for this last section. Okay, so let's start with some reminders about the GRANDMA collaboration and the gravitational wave astronomy, which is the main scientific domain. The GRANDMA collaboration has been built for doing this kind of science. So I didn't make this slide, so I apologize if I'm not very smooth, but I will try to give you the main messages of this each slide. So for those who don't know, actually the gravitational waves have been predicted almost a century ago, a bit more now, but Einstein in its general relativity laws, and it predicts that ripples in space and time could be emitted by masses having an accelerated motion, let's say. And almost a century after this prediction by Einstein, we actually detected these gravitational wave signals. This is the plot you can see here. I will not enter into the detail, but this is the kind of signal we expect from a merger of two compact objects. So two compact objects, it's basically black holes or neutron stars. And so this has been detected in 2015. So here it was a collision of two black holes by the detectors that are called LIGO, that are two detectors in the US, and there are also another detector in Europe, which is called Virgo. I will come back later on this. So it was a huge discovery, this gravitational wave discovery. And the Nobel Prize has been given in 2017 to the people who participated to build these gravitational wave detectors, and it is probably one of the most important discoveries made in the science this last decades. So gravitational wave detectors looks like these 3 pictures you have here above. So you have pictures of the first, let's say, LIGO Livingston detector, the LIGO, the other US LIGO detector at Hanford, and the Virgo detector here in Italy, in Europe. And actually, it is just, I would not really go into details, so maybe this schema is a bit detailed, but this is based on what we call Michelson interferometers, where you try to make interference between two light beams that are sent with the same laser here beams. The laser beams are split into different arms. And actually, the beams are reflected here by mirrors and just recombined here in a photo detector. And what you want to measure, it's when a gravitational wave passes through here the two arms, you will have a slight motion of one arm with respect to another one that will create actually an interference figure in the detector here. So once you detect a gravitational wave, this means that you have a light interference here in your detector. This is how we detect these things. And this motion between these two arms is super, super small. The type of, yes, I want to admit people at the same time. The type of astrophysical events that are supposed to create this gravitational wave signal. Well, we are going to talk about only one main event, which are the mergers of compact objects. So as I told you before, it can be a merger of two black holes that we call black holes, like typically objects that are right above the 5 solar mass object. This means that for these objects that collide, we are pretty sure that they are black hole actually. The other kind of objects that can merge into these systems are neutron stars. So we call binary neutron stars mergers, the merger of two neutron stars. And we call the neutron stars objects that have masses that are roughly less than 3 solar masses. Between 3 and 5 solar masses, we are not pretty sure about the physics, and we are not pretty sure if these objects are hyper massive neutron star or light black holes. So this is what we call mass gap. But well, this is a bit detailed here. Another kind of source that can emit gravitational wave in a merger system, it's a merger of course, a neutron star and a black hole. So you have this kind of astrophysical events that occur randomly in the sky and at any time. Yes, Sarah is here. I don't know if I didn't see her, but maybe she's here. So they can occur randomly in the sky and at any time, and we try to detect them with these all sky detectors that see the whole sky at any time, and so detect the gravitational wave signals. And these gravitational wave signal, well, events are unfortunately poorly localized by the gravitational wave detectors. So you have here a typical sky map. So you have here in the x-axis the right ascension, and here you have the declination here. And here the colored area here are the region that enclose the probability domain that enclose the gravitational wave source. So here you have here the limit of the 90% of probability region that contains the source here, the 50%. And as you can see, this is really poorly localized. For example, this 90% localization region, we are talking about almost 1,000 square degrees to cover. We are talking about localization that lie both in the north and the south hemisphere, and we're talking about localizations that are clearly not like point-like sources. So that's the challenge. The most of the part of the challenge of following up gravitational wave sources for detecting electromagnetic counterparts is about try to identify the right electromagnetic transient in this huge error box. Okay, I will move forward. So these are the typical distance we get from the last observational campaign from LIGO Virgo. So if you see here the plot on the right part, you have the typical distribution of the distances of the GW events that have been detected during the O3 runs. So there have been 3 runs of LIGO Virgo acquisition. The first one was in 2015, the detection of the first gravitational wave events. Second one was in 2017, and the third one was between 2019 and 2020. And so you can see that binary neutron merger are pretty close events, so roughly almost in the local universe, close to 100 megaparsecs, but we can detect up to 200 megaparsecs, let's say. While binary black hole mergers are very far away, cosmological, very extragalactic sources. This is a bit the schedule of the next run. So we have passed the 1 run, the 2 run, the 3 run, and we are waiting for the 04 run. This is all about, this is what the Kilonova-Catcher, why the Kilonova-Catcher project has been built, is to be ready for the end of 2022, probably the beginning of 2023, where the 04 run will start. And so there is an 05 also run that is planned, but it is more in back 4 years, let's say. So we are going to participate. So GRANDMA is going to participate to following up the electromagnetic counterpart of the O4 gravitational wave sources. And we would like amateur astronomers to participate with us to also identify, detect, and identify the electromagnetic counterpart associated to the O4 gravitational waves. And what are these electromagnetic counterparts? I will be very quick. I will try to be very quick. This is what we are talking about. So merger events of compact objects, and we are going to typically talk about 2 neutron stars who collide together, and that will expel some matter in the surrounding medium, and this matter can radiate electromagnetic counterparts, especially in the visible and infrared range, wavelength range. So this is here an image, here a catalog image from DSS catalog. And you have here an image of the LCOGT, the Last Cumbres Observatory Network, that took an image at this date where we discovered for the first time the first ever kilonova, so transient optical transient associated to a binary neutron star merger. And we call this kind of transient a kilonova. That is why we have called the project Kilonova-Catcher, to catch this kilonova. And typically, these optical transients are peaking at an absolute air-bound magnitude of minus 16. So in this case of this event, located at 40 megaparsecs, the peak apparent magnitude was about 17 in the airband. And this is a fast fading transient because after like a few days, these events are likely not to be visible again, observable by typical like 1 meter telescope or even larger telescopes. After a few days, you can lose several magnitudes. After 10 days, you are here at about 4 magnitudes lost. So it's a quite fast fading transient compared to supernova, for example. So this is a bit for the introduction. So about gravitational wave astronomy, what we are looking for. What about the GRANDMA collaboration? So just a reminder, I don't know if Sarah is here, if she wants to present this, but so I will start. So the GRANDMA collaboration is a collaboration of astrophysicists and observers all around the world. We are talking about 23 observatories linked together in the same scheduler, more than 30 telescopes, and we are talking about 29 institutes or scientific groups all around the world that are grouped together in this GRANDMA collaboration to perform optical follow-ups of these gravitational wave sources. So the main scientific responsible, the principal investigator of this GRANDMA collaboration is Sarah Antier. You all know Sarah, I guess, so I don't need to present her. So we have here a couple of links if you want to have a look of some publication we have made so far the last 2 years, mainly about our observational campaigns during the O3 run when the GRANDMA collaboration has been initiated. Okay, this is now short presentation of who we are in the Kilonova-Catcher team. So I just need to remind that the Kilonova-Catcher project is a citizen science project that has been made by the GRANDMA collaboration. So all those people, all the scientists here are people who belong to the GRANDMA collaboration. So the main people who are, let's say, managing the project are me. So you can see me here right now. You have Sarah, who is mainly responsible of communication and interfaces with GRANDMA. Alain Klotz, maybe some of you know Alain, who is our astronomer expert, professional astronomer in the University of Toulouse. Antoine Caillot, who is our also astronomer expert, amateur astronomer expert, who gave us a lot of advice for building some tools that are adapted to amateur astronomers. And we have also the web developers and our technical support at EGC Lab in France to maintain the website, etc., the web infrastructure. So we are a small team, but we try to make big things, let's say. And the goal is of the Kilonova-Catcher project is to link together the GRANDMA professional astronomers with the amateur, let's say GRANDMA amateur astronomers, and bind these two networks for two cases of observations. So this is about following up gravitational wave sources to search for kilonova candidates in this GW credible region, localization region. So for this, we need people who have large field of view telescopes, and we don't need a very accurate precision on the photometry. We just need people to take deep images and how many images as they can. This is the first case, to detect the sources. And once some sources are detected, we are going to characterize them to identify them if they look like kilonova candidates. So for this is characterizing the flux evolution of the kilonova candidates. And for this, we don't need large field of view telescope. You can do the job also with small field of view telescope, but here we need good photometry for the images. So we need high quality images here. You have here some links. I will not detail all of these links, but you have here some links to contact us. So feel free to contact us with any means you find better for you. Don't hesitate to contact us by mail also. So this is finished for this very long introduction. I'm sorry. Do you have any questions about that? Maybe a few questions. And at the same time, I will search if Sarah is around.
Yeah, Damien, hi everyone. Do you hear me?
Yes, I can hear you.
Okay, sorry, because I don't know if my connection is quite stable.
Okay, so you want to move forward?
I will do that, and if you think that you're not listening well to me, you can,
So you tell me next slide, and I will make the next slide.
So next slide, please, Damien.
Yeah.
So some of you participate to the Ready for O4 campaign that starts end of May and finished end of September 2021. And you can see on this link, I don't know if Damien forward the slides, but there is, with this link, you can go to look for our article that we have done from our observation from the 4 months of campaign. So finally, 37 telescopes were engaged and observed, including 26 amateur astronomy telescopes. So, I mean, some of you, maybe some of you were there, and we really, really would like to thank you for all your passion and patient time to observe this transient. These transients were, in fact, Kilonova candidates that first discovered by the Zwicky Transient Facility that we call ZTF as well. And ZTF, in fact, is a survey telescopes that observe large portion of the sky every night. And by observing the sky, we can detect variable stars or new objects that maybe are just asteroid or minor planets or supernova or transient astrophysical transients that we are look for in GRANDMA. And so during this, from April to September, 35 million of new sources, new triggers were detected by the Zwicky Transient Facility. And so the collaboration with Think, which is a French project, helped to filter this new detection. And based on our knowledge from Kilonova and looking for close Kilonova, we can filter from the 35 millions of detection, just 100 during April to September 2021, using criteria 1 based on the evolution of the sources, and 68 using criteria 2, which it's looking for kilonova in a nearby galaxy. On our side, we were very happy to organize this work with you. That is true that we struggle a bit to digest your flow data because there are very diverse data with diverse also quality and with different filters that we do not use much in professional in our professional area. However, so in fact, after this post September, we thought that we could submit our journal article in October, but it took really a while to adjust our analysis to your image. However, it is one of the first and maybe the first experience to follow up this Zwicky Transient Facility transient in the world, and we should be prompt really of that for rapid transient. I'm sure that maybe there is some supernova group around. So next slide, Damien. So this is the major figure on the article. We were sending to you, to Kilonova-Catcher, only alerts on Friday. The strategy was when an alert was coming on Friday, we were asking you to observe and to report your image, to upload your image in our server in OnCloud. And the idea was to follow up on Friday night and Saturday night and Sunday night to, in fact, be trained of how to respond to alert that can come on Friday, but still in at an unknown time, let's say, well, during USA night, of course, but at an unknown time. And so you see, Damien, can you put your mouse on the first transient? So you see, for example, this is chronologically. So you have in x-axis 0 is a trigger time. So the orange bar is a discovery time on ZTF. And then you have the first bar vertical line is 1 day. Then the second is second day post alert. and last is third day of alerts. And in orange, you have so one bar at 0 because it's a ZTF observation, and the second bar, like if we took the first alert at days 2, Damien, in orange, yeah, this one, yes. So this is the when ZTF reobserves the field. So it takes like 2 days at ZTF repoint. And the idea was that you guys, you're gonna feel this observation from 0 to 2 days. And this is what happened because we have a series of observation around 1 day for less than 1 day, 0.7 days, and another series of observation of 1.7 days, because most of the amateur astronomers that we have in Roma, and I hope it grows, is all located in Europe. So that's why we still need to wait that the night is in Europe. But it shows how your contribution helped to fill the gap of observation between the discovery point of ZTF and the second observation. And you can go through that for the different alerts, and you can see the benefits. I mean, your contribution mainly, how you can relax in less than a day, how you can see with your points how the how to say the transient is evolving. So what are now the circle that you saw? Because we talk about like the bars, the vertical graph, but now the circle. It's just that we calculate, in fact, the slope of the transient, if it is rising or not rising. And you can see in the first plot that the source is negative, so it's rising. And so it shows that clearly is not a Kilonova, because something that just rises and then is stable because it's still rising, show that it cannot be a Kilonova because it's rising, and maybe the rising phase of the supernova. And on the right side, so you see there are just vertical bars, but no circle, because in fact, he used the other criteria, which is not based on the Lie curve, but on a point that, there was a discovery on ZTF, you see at time 0. And the idea was to say, okay, we have a new discovery. Is it moving objects or is it an astrophysical sources? And your observation helped to guide us to understand if it is a very, very rapid fading transient that we could not detect, or if it is a moving object or something like that. And so this is why on the right panel, you can see observation of upper limit, so no detection point, that helped to rule out that it was an astrophysical, and let's say a transient or something like this, a point sources. So yeah, so congratulations, and we receive the report of the journal that is MNRS, so a London, UK journal that said that we need to change a few things, but it's going to be published soon. So thank you again for all this work, because it finally led to a publication. And for newcomers, so the amateurs that took data and help for the contribution of this article are also author on our article. So next slide, Damien. So now to go to still continue to observe, but to be a bit more efficient, some takeaway message. So first, again, a big thank to all of you, because this research couldn't happen without you, and this is really, really nice. Now some room of improvement. So we thought that there was some issue with the data. Or maybe Damien, you can jump in for this takeaway message 345. What do you think?
Yes, sure. So yes, so if you remember, so you send us some data, some images on the GRANDMA and cloud server, and then our task in GRANDMA was to analyze your image and to extract scientific content from your image. So typically the limiting magnitude of your image or the photometry of any transient you would have detected. We just have some few takeaway messages for making some improvements about your images. So we have, for example, some images that seem to be not flat corrected or not as well. Maybe there was a flat correction or the flat was not good or something like that. So it's super important for our analysis, for our scientific analysis, that your images are as much as possible pre-processed, so pre-corrected by the bias, the dark, of course, but also by the flat, as much as possible. It's sometimes also well, we can make it for the astrometry, but it saves us time if you are able to make the astrometry of your image, and you just have to pass your images through the astrometry.net website that will give you actually the astrometric solution of your image, and it helps us to just faster the scientific analysis. So for this, I'm not sure if everybody knows how to do this, to put their images into astrometry.net. So we can, of course, provide a tutorial for the Kilonova-Catcher users, of course. But also don't hesitate to ask other amateur astronomers who are aware about these kind of things or who knows how to do this. Don't hesitate to ask questions by mail or by Slack to everybody, like I would like to make the astrometry of my image, how can I do it? And people will answer, of course. But of course, you can ask you can ask us directly and we will answer to that. So this is really important if we have this kind of pre-processing or of your image before you upload them into our servers. If your image, so if you manage to push your image through astrometry.net, so to get an astrometric solution of your image, so to typically convert your X and Y CCD coordinates into right ascension and declination, if astrometry.net does not manage to find a WCS solution, so an astrometric solution, or if you see in your image that well, the sky was too cloudy, well, you took images, but you see very few stars in your images, do not upload your image onto the server, because probably we would not be able to analyze them afterwards and to extract scientific data from your images. That's the first thing. Of course, we had very beautiful images, so that's why we managed to make this publications I was talking about, and we really thank you for this work. And we can, well, if these people who manage to make very beautiful images can also teach to others how how they made their images, it can be very beneficial for everybody. Also, we concluded something very important about the photometry, so about the filter you use. And we find that it was sometimes pretty hard for us to perform accurate photometry of your detection, because some of you detected some sources. Once you use some unfiltered, well, once you do not use any filter, or once you use filter like a broadband filters, typically like luminance filter. It is complicated for us to make the photometry because we are trying to cross-calibrate your images with catalog images that have very narrow filter. And so we have a large errors when we do this kind of calibrations. So our advice when it is about characterizing the flux evolution of a transient. So once we have identified there is a transient source here, okay, it's fading. If possible, and if you have access to this kind of filters, our advice is to make observation with standard filters, so Johnson-Cousins filter or SDSS filters. So typically in UBVR I band or GRIZ band, if you have such a thing. This is in the case of characterizing the flux evolution of a transient. So typically what we have done with the Ready for campaign was this kind of exercise. We gave you some transients and we tried with you to characterize the flux evolution of this transient. And for this, we need color observations with standard filters to make an accurate photometry of the detections. So we can discuss about how to provide you such filters. There may be some room for discussion about that. Maybe some of you are already equipped with this kind of filters also. But in this case, we propose that you do not make well, this is a proposal you can make also, but to not make an unfiltered or luminance observation. However, when it will be about searching blindly optical transient in the localization region of the gravitational wave sources. So once we just search for something, of course, here we are going to use unfiltered and luminance filter because what we need is to have deep images. So we need sensitivity. So you can use unfiltered luminance at the first step. Well, at least the first point, the first detection, we just need to find something. So here, our advice is to, if you can make also colored observation, it's great. But if you can't, don't hesitate to use unfiltered and luminance filter for your observation when you just search for the optical transient. That's the main takeaway messages we had. Well, we can discuss. I don't know if there is another slide. No, so we can make a stop here if you want to discuss about this. I know that this is already a tricky point, the photometry.
Damien,
yeah,
I have a question regarding flat fielding. There is a possibility sometimes to remove remaining gradients on a picture through software. Do you want us to do that? Or do you prefer that we stop just after the flat field, even if it's not perfect?
Well, if so, you propose to make these kind of things after having made the flat correction, right?
Yes.
So the problem is that we are not sure how your software is behaving or how it's going to impact the image. So maybe if you have a flat, if you have a flat field, okay, it's not very perfect. You can just send your image like this.
Okay.
I think.
Okay, fine.
Also, I didn't mention that. I forgot to write this, but I think it's better also if you are not sure about to reach the needed sensitivity of your single images. Instead of providing your several single images, it would be better to provide stacked images. So one stack images instead of like 10 single images. If you are able to stack, I think we can also provide some tutorials for that.
On this matter, do you have a preference for what's the maximum exposure time?
Well, I mean, it's going to depend on your telescope configuration and the distance of the source also. So
yeah, but
the gravitational wave detectors will give us a distance. So, well, plus or minus some megaparsecs. But so we will have the distance of the source for when we will search for kilonova candidates. So we will know roughly the apparent magnitude we are expecting from the possible kilonova. So according to that, you will probably be the better person to know which kind of exposure you are able to do to reach this apparent magnitude with your own telescope. We can provide a tool maybe, but I think it will be too generic for being very specific to your telescope.
Okay, but so the alerts will include the estimated distance?
Yeah.
Okay.
Yes,
Okay.
you will have the estimated distance. What we can provide is, but I think we provided this for the ZTF ready for campaign. We provided also expected apparent magnitude based on this distance. If we had the distance, we didn't have the distance for ZTF. But yeah, this is something we can think about. It's to provide you the typical, let's say, apparent magnitude in the R band you would expect for this kilonova located at this distance. This is completely feasible. Yeah. Maybe it can help you to know at least if you have to make a very deep image or very deep exposure, or maybe less, well,
okay.
Smaller exposure. Maybe well, maybe we have some time if you want again for a few questions. Otherwise, we can move forward. But
just another question on my side. The astrometry data is included in the feeds header once you send it to the website.
Yes, once you send it to astrometry.net, it's going to insert into your header the WCS keywords. And so you will just have to download the new feeds file that is provided by astrometry.net, and then it's done for us.
Okay.
I didn't remember. I had some of you last time for doing this, and I think the person managed very, like, in 5 seconds to make it. But if needed, don't hesitate to ask us, like, okay, can you make a short video to show us, and we can make it. I don't tell you that we are going to make it in a minute, but we will try to make it, of course. No other questions?
I had one question about the filters. Are the filters which are used for astrophotography, which means color filter, but with a rectangular wavelength transmission, are those acceptable, or it's better to have really the more V-shaped filters for photometry?
You are talking of the biofilter, things like that?
Yes, I mean, people who do astrophotography have filters that really have a rectangular response. You know, it's 0 up to a wavelength, then it's 100%, and you go back to 0.
Yeah. Well, I mean, maybe you can provide us the typical shape of this filter, and we can answer to you. Here,
okay.
I will not be able to make you an.
You need to be able to do the calibration.
Sorry?
Between UBV, you need to be able to do the calibration between UBV system and the filters he is using.
Okay.
But typically, we make our photometric calibration with Johnson Cousins or SDSS catalog. So filter catalog. Yeah. So it's easier for us if your filters are close to this filter shape.
Yeah. But if they have a small wavelength range, that might be an issue.
Okay. No other questions, so I think we can move forward to the next point, which is the maybe most tricky point for me, because it's the website demonstration. So it's you know, once you try to demonstrate something, it's a source of error. So I will try to make you a short demonstration of different functionalities you could find in the Kilonova-Catcher website. You will see that we don't have so much functionality, but it's not a problem because I think it fulfills at least the main basic needs we have for this project. So can you see my my page here? The Kilonova-Catcher page?
Yeah.
Yes? Okay, great. So the website is at this URL here. I can provide you the URL again after this meeting. So be careful because we had an older website which is called Kilonova-Catcher.grandma. Something. This website is no longer available. Well, it is still open, but there is nothing behind this website. So the URL is really this one. So when you go to this URL, you will arrive on this main page where you will have to, well, either sign in or register if you have never made any account. So you can register here or log in here. You have also access to a frequently asked questions section that we will try to feed well, as long as we can, and as soon as you will, for example, ask us a question about what is messenger astronomy. So once you have a question, we can add here the question and the answer associated to this question. So for example, what are gravitational waves? We have some text. So we provide for each question a text here that explains, that answer this question, and some links also to, let's say, go further into that question. It can be videos, so like this, it can be videos, but it can be also some articles or publication, official publication, or it can be journal article or whatever. You have some materials here to try to understand better the context of this Kilonova-Catcher project. So if you never register, you just click on register. It's a kind of typical register formula here. You just have to indicate different things here. Don't forget to accept the term of use here. You can read the term of use here. Once you will click on register, you will receive an email. Don't forget to click on the link, activation link on this email to activate your account. And don't forget to check also your spam box in your mail. So once you are registered, you can log in. So I will log in with my own account. Okay. So, so you will arrive on this dashboard here. So on this, so you can verify that it's yourself, of course. But so once you logged in, you will arrive on this dashboard where you have typically two sections here. The section listing all the alerts for which you have joined the campaign. So here, for example, me, I have. So these are simulated alerts, but based on real old events that I just used to make demonstration. So here, for example, me, I participate to 2 follow-up campaigns. One follow-up campaign, which is here, normally should be written gravitational wave. So this alert has been detected by V1, which is Virgo. It will be more explicit afterwards. I need to change a few things. You have the date of this alert, so you can see that it is a very old alert here that I use for simulate this event. An important thing is here the counter. Here you have a deadline for which at which the campaign will be no longer available for following up, so for pushing images into the system. For gravitational waves, we are not sure really right now, but we think that we are going to put like 2 days, 2 or 3 days.
Nee,
there is somebody who is not muted. Can you mute your microphone, please?
ja.
Yes, great. Thank you.
Ja.
Wil je niet deporteren?
Niet direct.
I don't know, Sarah, if I can mute people. Okay, thank you. So here you have the type of events. So this has been mainly made for gravitational waves, but it can be used for other kind of transits. So here you, for example, can see the event type. So if you click on here, this will give you here, it's a binary neutron star merger. And here the number here gives you the probability that it is a binary neutron star merger. So here you are 100% sure that it's a binary neutron star merger. You have the distance here of the event. You have other contextual information about this event. So probability that the merger system hosts at least one neutron star, it's 100% because it's binary neutron star merger. The probability that the post-merger ejecta has been produced, so which is very important to, well, radiate some electromagnetic wavelength, we need to have a post-merger ejecta. Here it's 100%, so it's very important, very interesting event. So here you have the degree of interest for this event. That is detailed, will be detailed in a publication that is ongoing. And here you have the number of images that have been taken for this event and the number of the number of transits that are associated to this gravitational wave event. Here you have the observation plan that you will receive for each of your telescopes. So here I have an observation plan for my telescope, which is named My Telescope, which is a fake telescope. And if I click on it, I will receive my observation plan that I will not give you too much detail, but it's a typical CSV file that will give you tile ID. So let's say an ID for your observation and the right ascension and declination coordinates in different units, so HMS or degrees. And you have also other kind of information about this this target ID. So you have the probability that the event is inside this target ID, this tile. This will give you this will be given by this probability. And we will also give you the name of the galaxies that are inside each tile ID. So for each tile ID here, so here it's one tile, here it's a second tile, the third one. You will have a list of galaxies here and the name of these galaxies and the coordinates of these galaxies and their redshift, their distance. So this observation plan is the pointing we advise you to make, and they are ranked by order of probability metric, which is the probability that a tile contains the gravitational wave event. So they are ranked. So the first one is the highest probable tile to contain the gravitational wave event. The last one is the less probable tile. Okay. So once you have your observation plan, you want to see the alert, what the alert looks like. So you can click on display alert. So you will be redirected to another web page, which is the alert page for this event. So you have here the event name for which you are following up some electromagnetic counterparts. You have here the degree of interest of this event. You have the detection time of this event. You have the type of alert that this event is. So here it's written simulated event, but later it will be like gravitational wave. And you have the event type. So gravitational wave is the type of alert. The event type is the type of gravitational wave alert, which is here binary neutron star merger. Okay, so you have a sky map here. I'm going to give you some details about what is this sky map. So we try to find a fancy design to display things on this sky map. So you have here the sky that is visible at the time. So here you are just plus 0 hour after the trigger time. So you have the sky that is immediately visible at the trigger time, the time of the alert. And so in the sky, you have displayed in yellow, always, it will be always in yellow here, this shape, the localization region of the gravitational wave event. So as you can see, it's poorly localized and it's completely non-standard, let's say, localization region. We are not used to have this kind of localization region in astronomy, but now we have to deal with that with gravitational waves. The red points are the pointing that have been produced in your observation plans. So the pointings that we advise you to make. So here you can see that there are some pointings that are outside the gravitational wave localization region. It is just because it is completely fake, completely simulated. So normally all the red points should be in the yellow part here. So you can recognize some constellations here that are drawn from, so of course you can zoom in, that are drawn here in the yellow, in the white dots. So these are the stars, and you can recognize some constellations that may help you to, let's say, have an overview of the sky that is visible for you at that time. And the sky that is visible for you at that time is plotted in this blue region here. So this is the visible sky for you. We decided to put an horizon limit of 30 degrees. So here it's the horizon limit for 30 degrees. So here you have the position of the moon, where the moon is. And the circle here is a circle of 20 degrees, I think, around the moon. And here you will see that the moon is not completely full. And the circle here representing the moon will be more or less full depending on the phase of the moon. And here you have the sun, the position of the sun here. And finally, the last thing you will see on the sky map is the position here of the galactic plane on this plane line. And here you will have, I think it's plus or minus 20 degrees above the galactic plane latitude. Okay. So typically you will see, you will understand that here it's going to be complicated to observe. So we will not provide pointing here. Here it's probably complicated also to find something because you are in the galactic plane. So probably you will better favor this region here. So all this plot here, as you can see, is surrounded by yellow color. This yellow color is to tell you that you are at your local time where you put your observatory. At this time here, at the alert time, you are on the daytime. Of course, you can see it if you are outside. But if you can change the time to just go 24 hours after the alert to just foresee what will be, when will be the night for you, and how long it's going to be observable also the source for you. So you just have to change the time. So here we'll take plus 11 hours. I will submit. Just don't forget to submit. So now you can see that the background has changed. It is now in the night color, and this is written night time for you here. T0, so T0 it's the alert time plus 11 hour. As you can see here, the position of the sky has changed. So everything is moving depending on the time you choose. So if I just put 0 to, you can see that the time has changed. I guess you see. And you can see the position of the sky has changed. And so this will help you to just foresee when your tiles will be observable for you, when you can go out and take images at the best time for you, etc., etc. You can at any time download the sky map. So you just click on download and you will have this PNG file that you can open at any time. If you want to visit the configuration here, well, you just reset normally the zoom. If you have several telescopes, so me, I just have one telescope. But if you have several telescopes that had like several observation plans, you will have here a list of your telescopes, and you could choose your telescope and have a sky map for each of your telescopes. So you could really see the visible area of your alert for your telescope located at the place you register on the website. So here, me, I've just put fake things, fake informations for my telescope. Okay, so you have here the key to understand all these different patch plots in this display. If you go below here, you will have your observation table. So these are the tiles, so you can recognize here the target ID or the tile ID that is also provided in the CSV file I showed you before. So these are just the different tiles we advise you to observe. As you can see, they are ranked by their metrics, so the probability that the event occurred in this tile. So here, the top tile is the tile that has the best chance to host the gravitational wave event. So here you will have some, for each galaxy that will be in this tile, you will have a button that will redirect you for each galaxy to the Simbad catalog. I don't know if you know this website, but it is provided by the Strasbourg Observatory at CDS. And so it will give you all the information of the galaxy and also some small visualization of the field here. You have the number of the images that have been taken for this tile. And here, normally, you should have the name of the people who observed this and the date at which the people have observed. So your goal, your job to you is to take some tiles here. So you have the coordinate of the tiles to make observation with your telescopes. And once you have image, for example, for this tile or for this one, we can try to push, I will try to push for this tile. For example, I made observation for this tile. So you click on upload fit and it's going to link your image to this tile. It's very important. So don't upload everywhere. So just use the right tile that corresponds to your image observation. So here I will upload a fits and you will arrive on this page where you will just drag and drop your files. So if you have so here you can just click also directly on this, directly here. And I will push one file. We just accept only the .fit or the .fits file extension. We do not accept JPEG or whatever other files because we just don't use it for analysis. So I will push this, for example, test fits, or maybe this one, new fits. So here it's loaded. So it's correctly loaded, but you have here a red message that tells you that your headers are not okay. So once you have this message, don't panic. There is a way to correct this by clicking on this. I will go to this tab after, but I will just show you once it is also working well. So if I will push test fits. Up here, headers are okay. You have uploaded your fits file. It's finished for you. You can upload another file. You can upload 8 files at the same time. Do not upload zip file or archive file. We are sorry, we do not take into account this kind of file format for now, but we will probably change later. So I will come back to this header that are not okay. So you have here, so you just click on this here. And you can find the same thing here. Actually, it redirects you to my observation tab here. Once you arrive here, you will have the list of the files you have taken for all the observations, all the different alerts. So you can, so for example here, I will come back, sorry. You have uploaded a file for this event, so you can copy paste here. And if you put here all the files that you have uploaded, all the observations you have made for this event, you will have the list here. So here you can recognize the test fits file that I pushed like 30 seconds ago. You will have a green button valid when the headers have been checked by our code. And you have nothing to do. If it's valid, it's okay. If you have a red button click showing modify, this means that there is a problem in your header. And here you can directly see that probably there was no right ascension or declination keyword in your header. And we can't analyze your image if we don't have these keywords. And there are also other mandatory keywords that are provided, but very few. So you just click on modify here. I will just modify this quickly. I will put 54.7, for example. I will here put, let's say, up this. You can change the date. So these are the keywords actually that are mandatory that you will have to find normally in your header. If they are not, we can't analyze your image. The filter, you can choose amongst different kind of filters. So here, let's say we take urgency filter image to submit. And your observation has been modified. You go back to observation, and here it's your new fits file that is now valid. Even if it's valid and you think that, oh man, damn, I've made a mistake, you can go back here and still continue to modify if you were not sure. Like here, I will submit again. And here, once you have made this, so it is written the observation has been modified, and you still have here a list of pending images with bad headers that you need to modify. So this will give you the list of things we expect you to correct. If you don't correct your headers here, so we probably won't be able to analyze your image. So it's very important that you provide either good headers or you correct by yourself the headers afterwards. Okay, so this is the main things, the main functionalities that are implemented yet. If I come back here, I just can make the summary. So here, campaign, display alert. You will be able to scroll on the different times you want for the different telescopes you want to see the sky map, and upload your images on the tile ID that has been provided to you. I've made a simulation of an event that will look like for the next thing, the next point we discussed. If I have time, yes, we have still 15 minutes. Here I simulated another kind of object. So you can see it's a ZTF transient. It's a real one. And actually it has this optical transient has been identified as a gamma ray burst afterglow. I'm going to talk about this later. But these gamma ray bursts are well localized. We'll show you the alert display after. But you will see that for these kind of events, alert type that are not gravitational wave, of course, we have no information about the distance, about if it's a binary neutron star merger. By default, it's PNS, but you can see here the probability is 0. And we have no information here and here. But we just want to, it's just to tell you that we are able to provide you alerts of different types, more than just gravitational wave. And if you click on display alerts, you will have exactly the same display. But instead of having, you know, this large yellow localization region, you will just have a point here, because it's a point-like source that is well localized in the sky. So you have just this point. And as a tile idea, you just have one coordinate. And the metric, the probability that the event occurred in this target is 100%. And so you just have, at least for this one tile, to observe one pointing, and just you can just upload all your files here, and it's exactly working the same. So why we did that? It's because here, in this case, as you understand, we search for typical, we search blindly optical transient in this large localization region. But in the case we have identified a transient, and a well-identified transient, we could be able to provide you another alert that could appear here. And in this case, you will have a new observation plan, which is just one pointing to follow. Would be maybe easier to deal with that. So this is for a campaign you have joined. You have another section that is not shown here because there is no pending alerts waiting for you to be follow up. But once you will have new alerts, they will be stored here in the same kind of table here. But just like instead of display alert, you will have join campaign button. And once you will click on join campaign button, sorry, this alert, which is pending here, will just go back to this table, and then you will be able to display alert, etc., etc. As you can see here, we have added 2 images, so we are now 6 images taken for this event, and here 5. Just a word, maybe last word about how to register your telescope into the system, which is very important. We are going to build observation plan for each of the telescopes you will register on this website. And you can do it by going to this telescope here, click on add telescope. And you have several information to provide in this formula: the name of your telescope, the alias of your telescope you want to give. Each red star here, it's a mandatory field, so you have to provide an information here. You can here give the type of telescope you have. For typically for you, it will be visible, or if you have an infrared telescope, well, the telescope is not infrared; it's a camera or the filter. But anyway, the aperture in meter here. For your observatory, of course, you will give also a full name, but we will probably use the short name to display information about your observatory. The latitude and the longitude of your place where you put your telescopes. And we are very sorry, we still didn't corrected the mistake here. So the rule here is not correct. It should be minus 45 for Western longitude, and it should be plus here for Eastern longitude. We just have reversed the standard, let's say. So we are sorry for that, we have to correct this. But here, don't forget that it's minus for Western longitude and plus for Eastern longitude. Elevation in meters, if your observatory, if you have a website, or if you use a telescope that is from a public, no, this would be another kind of things. If you have a IAU code that you can provide, and the same thing for your instruments. Okay, I think it's pretty easy. Here, if you have no idea about the limiting magnitude you can reach in a typical exposure, this is useful for us if you could provide this kind of information. If you can't, just put some value, maybe a fake value, and we will just do not use it like a minus 10,000 and something like that. And just you click on Add Telescope, and your telescope will be registered, and you will be able to see it in the list of your telescopes. So here it's, for example, the list of my telescopes. So you have here the coordinates of my observatory, where my telescope is linked to this observatory. You have here the information about my instrument, my camera. You can modify this information at any time. So here you can, if you want to modify the information about your telescope, or about your observatory, or about your instrument, you just click on Modify Telescope. And here, as you can see, you will be able to modify things. And just click on Modify Telescope, it will modify your information. You can add another observatory. You can also add another instrument connected to the same telescope. If you want to delete also the information, you can delete everything. Final thing, some of you have access to public network of robotic telescopes, such as iTelescope.net or the AAVSO network or something like that. If it is the case, you will be able to send images from this telescope to the Kilonova-Catcher website by just joining a collaboration. So for example, here I will quit this collaboration, I will show you. So we will have a list of collaboration that probably some of you have access to. Put more collaboration, you will have to tell us which collaboration you are able to join. Well, you are able to join physically, so that us in our side, we will add it into our system and you could join this collaboration. So here I just added iTelescope, for example, and I just put 3 remote telescope that some people have access to, but if you have access to other iTelescope, just tell me and I will add them. And once you join this collaboration, you will have here observation plan that will be produced for these telescopes. So here I didn't produce any observation plan for this telescope, so that's why you don't see here iTelescope 8 or iTelescope 30 here. But once they have observation plan, you will be able to download the pointings and make the observation with these telescopes with the list of pointings. You can go back to the history of your previous observation about the previous alerts you observed. So currently there are 3 simulated alerts in the system. So me, I just, of course, participate to all of them. And so if you click on this, you will have just some informations. I will let you go into the detail of this. You can click on observation list and you will have access. Oh, there is nothing here. You will have access to the observation that has been made for this event. So here for this DET-TF event, you will see who made observations. You will be able to click on this link here to see the feeds file, so the image of the user has posted on the Kilonova-Catcher server. So maybe I will choose another one, which is this one is a bit dirty. Okay. I don't know if I have another one. Okay, maybe you can see this one. So by default we put blue, but if you will be able to dig into the details of this display. But you will be able to have a look of all the images that are posted by all the users for different events. Also, you will be able, for your observation, to relook at your images by clicking on this button. I think I will stop here. These are the main functionalities we have in this website. So provide information about your telescope, wait for an alert and an observation plan for your telescope, go into the display alerts page, and just upload your FITS file into the dedicated tile ID that is connected to your observations and also to your telescope.
A question.
Yeah.
Shall we have already alerts on our phone?
On your phone?
Yeah, by Slack?
Yes, yes. So the alerts will be also provided by Slack. Also, for some of you who registered and click on I want to receive alert email, you will receive alert by email also.
Okay.
And you will be able, once you register, you will be able to change this. If you think that, oh, you are too spam or something like that, you can just remove the alert by mail and you will never receive an alert by email. But the minimum will be Slack, the website, and optionally, if you want, the mail.
Okay.
I had two questions.
Yeah.
First is about I was puzzled by the limiting sensitivity or magnitude that you can see. You know, it's what signal to noise ratio do you decide? And what length of imaging, you know, whether you take a 2-minute picture or you image for 2 hours and you stack your image, you get to very different sensitivities. So when you state sensitivities or limiting magnitudes, how do you state it?
So, so you are asking about what kind of signal to noise ratio you have to reach actually. So typically for us, we claim a detection of a source. So we expect the detection of a source. If you have a signal to noise ratio of about 5. So
okay.
So I can't tell you because it depends on your telescope. You will reach, if you have a large aperture telescope, you will reach this signal to noise ratio faster than someone who has a small aperture telescope. So it's hard for me to give you a typical exposure time for your image or typical duration of exposure for a given event, because it's going also to depend on the distance of the event. So you can see here, for example, this event was at 156 megaparsec, but we can have closer events that will be brighter, so you don't need to have such exposure time.
Okay.
So to me, I think we have to also, in the GRANDMA side, to think about this, because we always have this kind of question. I understand this question. And we have to think about a procedure that can be generalized to at least more or less to any kind of telescope aperture, because it really depends on the different configurations of people.
And the second question I had, you know, if you have a big CCD, you know, the FITS file can be very heavy. You know, it can be 20, 30 megabytes. So do you crop what is not significant, or do you like us to rebin to minimize the size of the file?
By cropping, you said that you mean like we just keep a part of your FITS, or
yes,
because here, for example, if you look at this sky map here, you can see my screen. Yes, if you look at this sky map here, you can be sure that even if you have a big CCD, the full image will be important, because we are going to search in your full image if there is something.
Okay.
So we need the full image. I know that if you have a big CCD, the FITS file can be super heavy. I know that. We have to think about this possibility. Maybe we can split the image into several parts. This is something that is not thought yet. For now, the maximum size we allow is 120 megabytes per file, which is probably too small for very big CCD files. I just received like 200 megabytes files. So this is not an unsolved problem for now, but typically we want to keep all your we want to keep all your fits file if we are searching, blindly searching an optical transient. But if we have already detected something, somebody has detected something, and we want to characterize it, of course, we don't need the full field of view of your image. So if you are able to crop it and to provide a maybe smaller image, in that typical case of characterizing the flux of a transient, maybe it's better.
Thank you.
I have a few questions about the sky tiles. Are they shared among different users? So we all get the same tiles basically, and if that's so, what is the typical size? Because I mean, different telescopes will have different field of views, and if my field of view is smaller than the size, am I encouraged to tile the tile basically?
Yes, I see the point. So it's still not fixed in our head, let's say, in our mind, these kind of things. But first, we are thinking of providing the same list of pointings by different time zones. So, for example, people that are, like, say, in the Europe, France, let's say Central Europe, etc., will have the same kind of tiles to observe. And people that are in another time zone will have another kind of observation list. That's the first point. We are thinking of making this. We are open to discussion, of course, about that. Concerning the size of the tile, it's complicated to give you a fixed size of the tile. So what we are just going to provide is to provide central coordinates for each tile. But of course, if you do not cover the same part than your neighbor, I mean, it's complicated for us to give you right now, but we can think about the solution, very dedicated tiles to your telescope configuration, like the same size of your field of view, etc., because we will have so many telescopes that it's going to take a long time to produce all these observation plans for everybody in a short latency. We have also this issue for GRANDMA. We are working on this because we have a lot of telescopes and we want to provide observation plan roughly at the same time for everybody. So we are thinking about solution about this, but it's, to my knowledge, it's still not completely fixed.
Cool, thanks. One other question about the FITS header about the time. So most of the stacking software I use rather give a central time and a duration. Is that okay, or would I have to then change that to start and end?
So I have to note this question. I will maybe answer by mail or later, but if I remember well, the keywords we analyzed are, for example, we analyzed the dat ops, X time or something like that, the exposure. But I think we also analyzed if you have a dat end or something like that, we also analyze it. But some of you will probably provide headers with mid time, something like that keyword. I'm not completely sure if we analyze this mid time. I need to check the code for that and to, before answering, give you a firm answer about that.
Okay, cool, thanks.
But these are the typical keywords we look at.
And what about filters? Do you expect also that information to be included in the FITS header? And,
yes.
And if so,
yes.
what kind of? Yeah.
So if you look at the, for example, I will take just one randomly. If you look at these are the typical keywords we are going to check into your FITS file. So if you have a right ascension, declination, so it's typically RA, DEC, or OBJRA or OPDEC. We have several kind of keywords we check for the same data. So these are the typical datops or dat start or something like that, some non-standard keywords. Here it's we compute datops plus exposure time, something like that. Or if we have a daten, we keep this daten as a time hand. And as you can see, we have also the filter. So for the filter, we have made the work to try to have all the kind of filters you could provide, like let's say R Johnson with different space after Johnson, R Johnson separated by a slash or something like that. We have tried to make a different configuration so that you will not have to modify your header each time you post your images. So these are all the kind of filters that we have into our database. So we try to recognize into your headers this kind of filters. If we don't have them, we just once you will post your feeds file, you will just have a red button telling you to modify your header, and you will see that if the information about the RAR, the deck, the time start, the time end is correct for you, this is probably because the filter is not recognized. And by default, we will put clear, I think. So if it's not clear, you have to change.
Okay.
But yes, we check the filter.
I have another question here myself. So on the filters you mentioned, you wanted us to use the photometric filters, but say for doing the searching, do you want us to search using the photometric filters, or should we search like using a clear luminance filter, and then once a target is identified, then use the photometry?
So once the target is identified, so once you have detected something interesting, we really advise you to use colored filters like standard photometric filters. But before, once you are searching, well, maybe here it's my personal opinion, but I would say first to use maybe the filter that give you the most sensitivity possible. So which is no filter or large or broadband filters like luminance or something like that. That's my personal opinion. I would say that just to search first. But the drawback of this is that once you will detect something, if you detect something and you would have the possibility to detect it with a colored filter, this means that we may maybe lose this very first point, which is also very important for colored filters. So I don't have a strong opinion on that. I'm not sure if my colleagues are still connected, but if they have an opinion about that, because colored filter, I mean, if you use broadband filter or unfiltered observation, maybe it would be hard for us to make the photometry. And the problem is that if you detect something, the first point is very interesting. So it's complicated to answer this, but maybe we need to think more about that.
So if we say we use a luminance filter and then we upload our images.
Yeah.
So you guys then look at that to identify the target, or are we supposed to? I mean, the uploaded images, you search them for a target in there. That's not up to.
No, we will search, we will analyze your image in real time, well, near real time. Okay. And we will provide the results if we find something inside your image that's typically a new transient source.
Okay.
If we find something very interesting, so once we will find something, we will try to take another observation. So probably we will ask you to take another observation of the same field to just see if the source is fading or if it's like not a cosmic ray or something like that. If it's not, then we will probably, well, we have to think about that. The strategy is still not completely fixed, but we will probably push another alert into the system, into the campaign. But the target will be maybe the name of your target that you have detected. And here we will ask people to make a colored filter, like photometric observations.
Okay, thank you very much.
So we have to train ourselves. So you from your side, but also us from our side to find the best strategy to, yes, communicate informations and be sure that you are using the right strategy, whether you are searching blindly for something or whether you are searching to characterize the flux of an identified transient. We have to think about make smooth communication between each other. Yeah. So, and it's still not fixed, and that's why we are not going to have time to talk about that, but that's why we plan to make another training campaign this month and also on May to train ourselves to communicate each other the different information. So maybe I think it's time to stop here on that side at least. Oh, sorry, I didn't want to mention my screen. Keep your questions and don't hesitate to send them by email. I promise that I will answer to all of them, but I will try to make it on time also. I'm sorry if sometimes I'm late in answering, but just keep your questions and we will try to answer them. We have identified something also from our side to think about better, especially for organizing the observation plans and to communicate the different strategies. So this is in our mind. I think, I'm sorry, as usual, we are out of the time, so I think we will not go into the next point. That was an interesting point, but which was a presentation to give you an idea of the next training campaign we would like to make. I don't know if Sarah is still here connected, but I think we will not make it tonight because I think it's going to be too late and there are already many informations given. I will see if, is she still here?
No, she left.
Okay. She was tired. So okay. Except if you have time, but I can make it if you want. In let's say in 15 minutes, I will try to be very fast. So maybe I can. Well, I will try to give you some information. Let's go. We just improvise a bit. So to train our. So if you remember. Last summer for the ZTF Ready for campaign, we trained ourselves to characterize the flux evolution of a given transient. So this was our first time we tried to train on this. So we just have one pointing to do and try to make the best photometry we can. And so we think that we need to check, well, if you are able to provide more images on different kind of transients, but still it will be the same kind of training ourselves on characterizing the flux of fast optical transients. And typically gamma ray bursts are one of the fastest optical transients you can find in the sky. So we plan to organize this. So I will move to this slide. So as I told you, the goal of this new training is to practice again to have fast responses to a GRANDMA alert. So GRANDMA is going to forward you this alert through the website Kilonova-Catcher via Slack or via email for those who want to receive email. So train your responsiveness. Train also our ability to hold together GRANDMA and Kilonova-Catcher to characterize the flux evolution of a transient. So here gamma burst afterglows. Train also yourself on using the KNC website functionalities on real conditions, and probably you will find a lot of problems or things you would like to be improved. So this is also a way to give us feedback about this Kilonova-Catcher website and the system we are trying to set up for the main objective, which is the O4 run by the beginning of 2023 for gravitational wave sources. So this is still a training session. This is still best effort, of course. And so don't hesitate to participate with us. So which kind of targets are we going to follow up for this training campaign? we are going to follow up sources, so-called gamma ray burst. I will not have time to go into the detail of the physics of gamma ray burst. I have some slides in here in this presentation. I will just tell you a few things. But these sources are detected by a satellite called SWIFT, for those who know SWIFT satellite, which is a NASA satellite. And these sources are like the ZTF transient, detected at any time and at any place in the skies. And by any place in the sky, I mean it can be detected in the northern hemisphere or in the southern hemisphere, because the SWIFT satellite, and especially the BAT instrument that observe in the gamma ray wavelengths, has a very wide field of view, because gamma ray bursts are very rare events, so we need very wide field of view to detect them. That's why we detect them all over the skies at any time and at any place in the sky. And so typically what this satellite is doing is going to detect this gamma ray burst in gamma rays and give a first localization thanks to the BAT instrument, which is the main trigger instrument of SWIFT in gamma rays. A first localization within 3 arc minutes. So this is very well localized sources. So it can be observed by all of your telescopes, I guess. And then typically few tens of minutes, few minutes after, you will have an update of this localization given by another instrument on board SWIFT, which is called XRT, which is an X-ray telescope. And that will give a few arc seconds localization accuracy on the gamma ray burst position on the sky. So here it will be very well localized. So there is no need to make tile. There is no need to spend time to search for something that is unknown. The SWIFT satellite will provide us these targets. And of course, we will have additional arc seconds localization accuracy provided by you or by other telescope on ground. Professional telescopes are searching for these optical transients all over the world, and also GRANDMA will make these searches. So we will provide also some arc seconds and optical images of these sources. I will not go into the detail, but for the physics, gamma ray bursts are emitted by massive stellar core collapse, what we call long gamma ray bursts. Typically, they last more than 2 seconds. And they are actually produced by very specific type of supernova that we call hypernova or supernova type 1b, 1c. And another type of gamma ray burst called short gamma ray bursts are likely produced by the mergers of 2 compact objects. So here you also see the link we want to make with the gravitational wave sources, because short gamma ray bursts are probably the first electromagnetic counterpart of a binary neutron star merger. They produce collimated, so once the star exploded or once the merger has occurred, they produced here a jet that is collimated because it's traveled at ultra-relativistic speed, so it's a jet of plasma that propagates into the surrounding environment and that produce a series of electromagnetic signatures. But what you have to know is that gamma ray bursts are the most luminous transient event in the universe. They are located at cosmological distances, so they are very, very, very extragalactic sources, but thanks to their very luminosity, we can observe them with decent apparent magnitude. Some of them, so the short gamma ray bursts, are connected to gravitational wave merger sources. So for our April to May training campaign, we won't have gravitational wave detectors available. So we just rely on the SWIFT satellite to detect this electromagnetic gamma ray counterpart and also X-ray and optical counterparts. Well, they shine first in gamma rays. That's why we detect them in gamma rays first. And then they shine at all wavelengths, and typically in the X-rays and then in the visible range, infrared, and then weeks later in radio. Some can be very, very, very bright at optical wavelengths, up to magnitude 5 for very few of them, at very early times after the first gamma rays photons, typically few hundreds of seconds after the gamma rays have been produced. But typically we can detect this gamma ray burst afterglow So in the visible magnitude in the range, like in the red magnitude, so in the, let's say, Hutchinson cousin magnitude, between 14 for the brightest to 21 for the faintest GRBs at early times. By early times, I mean few minutes to few hours after the gamma rays have been detected. They fade very quickly with a fading rate greater than half a magnitude per day. In the very early times, in the first hours, they can also fade at an incredible rate of several magnitudes per day in the very first night or very first hours. So this is very fast fading transients, much faster than kilonova that we are searching for the gravitational wave sources. So you have here some nice links or some nice video that is going to give you more details about gamma ray burst phenomenon. I encourage you to just click on this link or to ask us questions after this meeting. Don't hesitate, but these are very extraordinary sources, and they are connected to gravitational wave sources. That's why we also choose them to be our next type of targets for the follow-up training campaign. So when do we start this campaign? We will start with you by mid-April. So when I'm saying with you, it means that we are going to start to send alerts, let's say by mid-April 2022, through Slack, through the website, by mail for those who subscribe to mail alerts. Typically, Swift is detecting 1 gamma ray burst per week. So you do not expect to be spammed by a lot of alerts. There will be roughly 1 GRB per week, but be careful. Sometimes it can be 2 per day, 2 per week, 0 per week. So we have no hands on this. So we can't manage on this, but it is at your best effort to do what you can, and it's okay. When do we stop? End of May 2022, we will stop this campaign. We will analyze all the images and just make a feedback again as we did for the Ready for campaign. So how the alert will be sent to you? So through our Slack. So if you didn't register to Slack, there was the link to register to Slack in the very first slides, by email or via the Kilonova-Catcher website, as I said. How will you send your image? Yeah, well, via the Kilonova-Catcher website only. We will try to not use OnCloud at all now for the Kilonova-Catcher project. We will use the Kilonova-Catcher website to collect all the images from all the users. I tried to make a tutorial just a few minutes ago. We will push this tutorial online so that you can just replay it and just have a look on how to make things. Don't hesitate also to ask us questions like how we can do this, etc., and we will of course answer as soon as we can. In case of a failure of the website, if the Kilonova-Catcher is not available or if there is a functionality that is not working, so for now the FITS file uploading functionality has an issue where it doesn't allow the users to put more than a 1 megabyte file. We just have to improve the size file configuration in the website so that the user can provide a larger file. So for example, there are this kind of issue, but if you find an issue, don't hesitate to report this issue to us also. But so in case of failure, we will recreate an OnCloud repository for a given GRB, gamma burst, that as we did for the Ready for campaign. And you will be able to push your images here, waiting for us to fix the problem with the website. So for now, the website is working well, except that for the FITS file uploading, we have to just correct this 1 megabyte limit. So what are you expecting from us for this training? I think you are expecting from us to give you more feedbacks on your images. You are expecting from us to analyze your image to extract some scientific content as we did for the Ready for campaigns, and to possibly have a publication related to a given gamma ray burst. And of course, all of you that contribute to this follow-up campaign and for which we also use your image, will be in this publication. So this is, I think, a source of motivation. Maybe more things you expect from us, don't hesitate to ask us more things, or to try to see what we could provide to you, educational content or things, tutorial, etc. Don't hesitate to ask. We try to collect feedbacks and we try to answer one by one and to solve things one by one as soon as we can. And as usual, what we expect from you for this training is to give us also your feedback about the Kilonova-Catcher project, the Kilonova-Catcher website, all the communication channels, things on organization stuff, etc., etc. And we expect also from you to provide us images that are pre-processed as much as you can, so dark, biased, flat fit corrected. If you can make the astrometry, it would be very helpful for us to faster the image scientific analysis. This is very important for us to analyze your images. That's the only information I wanted to give you for now about this training campaign. I think we will make an official email once we will be ready to send everything, etc. And then you will be, so everything will be more explained in this email, and you will be able to, if you want to start your observation of the future gamma burst detected by SWIFT. That's all for us tonight. I don't know if you have more questions, maybe few questions, 1, 2, 3 questions before we go to sleep for the European people.
No, thank you.
Thank you very much, Damien. It was very interesting.
For the French, I'm so sorry for the non-French people, or maybe you will have so you the non-French people or European people will be able to go to Besançon city in France in June, but we will be at the SF2A Pro-AM Gemini workshop at Besançon in June to, well, present the Kilonova-Catcher project again, but especially this gamma ray burst training follow-up campaign. Probably we will have the first feedback of the analysis of all your images, so we will try to be here. We will be here at this event to meet you, at least the French guys, maybe others if you are able to join. I doubt about that, but I'm sorry we are not able to travel. Well, we are able to travel, but it's complicated to be all over the world. And hopefully we will be also in Paris in November 2022. It's not sure yet, but maybe. So to meet us in real, it's really also interesting. Virtual Zoom, it's cool, but meeting people in person, it's better. So if you have no other questions, we can close the meeting. If you think about questions after this meeting, don't hesitate to post it on Slack or via email. Don't hesitate to send us an email.